Climate change is a problem that we face every day and will continue to face for eternity if we don't change something. Our world requires a long-term solution for climate change, and we need it fast. Day by day, conditions worsen, making it harder and harder to find a solution. While doing research for my project, I came across an option that can help us combat climate change, which has mostly been overlooked, called solar geoengineering. Solar geoengineering proposes that we use different methods of reflecting sunlight and solar radiation back into space. There are many different proposed methods of solar geoengineering, such as marine cloud brightening, which is a method that uses sea salt and other ingredients to brighten clouds, increasing how much sunlight they reflect. Then we have microbubbles, a method that suggests using perfluorocarbons to mass-produce bubbles in the ocean, causing more reflection against sunlight. We see that these methods all have flaws, however. For example, marine cloud brightening requires a lot of materials because of clouds being temporary. In terms of microbubbles, we are unsure what the effect of microbubbles will be on the ecosystems and the marine life under. We then arrive at a controversial method of solar geoengineering that could be the key solution we've needed if it was executed properly. This method being stratospheric aerosol injection, and it is what I decided to focus my project on. What is it exactly, though? Stratospheric aerosol injection refers to using a fine aerosol spray. An example of this could be a Febreze in the stratosphere to reflect sunlight and solar radiation. Where does this idea come from? We see a similar effect during a volcano eruption. In a volcano eruption, millions of tons of ash and other chemicals are released into the stratosphere, initially raising the temperature. However, after the temperature returns to normal, the chemicals released by the volcano create a reflecting effect against sunlight and solar radiation, which can last for up to a decade. The main chemical involved in this reflecting process is sulfur. While sulfur is a good option to increase the albedo of the stratosphere, the negative effects of hosting sulfur in the stratosphere are far more profound, thus eliminating this option entirely. When sulfur exists in the atmosphere, it mixes with clouds and creates acid rain. While trying to solve climate change is important, creating issues such as acid rain in the process, which are known to harm the ecosystem that exists on Earth, is counterproductive. Before I talk about the rest of my experiment, it is important to look at a key component in stratospheric aerosol injection, or spraying aerosols in general. I am talking about how the liquid in the aerosol turns into a spray, through what is known as the propellant. The main propellant currently being used is HFCs, or hydrofluorocarbons. Although this is the most popular propellant, it is not the most eco-friendly. HFCs contain carbon, which is not a reflective ingredient, but an absorbent. This means that HFCs absorb a portion of sunlight and radiation, keeping it in the atmosphere, which leads to the temperature increase. Not only that, but they also contain traces of sulfur. For this reason, I researched different, more environmentally friendly propellants and came across the solution of bag-on-valve, or BOV technology. BOV proposes using a bag made of laminated aluminum and having the liquid being propelled by oxygen and nitrogen, two chemicals that we already see in the atmosphere. Through my background research, I concluded the following. The concentration of sulfur used in the current trials of stratospheric aerosol injection is the key reason why it is a less attractive solution. Sulfuric acid exists in both the propellant as well as in the aerosol. While it may be a necessary ingredient in the aerosol because of its unmatched ability to reflect solar radiation, it is not necessary in the propellant whatsoever. By removing sulfuric acid from the propellant, the concentration of sulfur can be reduced significantly. Using BOV technology, I will be able to dilute the concentration of sulfur and sulfuric acid that goes into the stratosphere, and I will be able to mitigate the risks of stratospheric aerosol injection as much as possible. But why is all of this significant? And why did I choose this topic? I did this project because I know climate change is a pressing issue that we will not be able to get rid of whatsoever without a concrete solution. And this topic could be a crucial breakthrough in terms of climate change. Because the current solution I proposed has detrimental effects on the environment, I look to use an eco-friendly aerosol that does not have negative effects on the environment and the atmosphere, which is where I found bag-on-valve technology. BOV can help us make this method healthy for the entire Earth, and can make it a solution that can be considered and can be used with little to no side effects. I hypothesized that the saltwater bowl with the air salt will have a lower temperature than the pure saltwater bowl. This was because of the reflective properties of the air salt and its capabilities of reflecting the light, unlike the pure saltwater bowl. In order to find if bag-on-valve technology can work, I decided to conduct an experiment in which I put salt water in 2 bowls and sprayed one with the BOV air salt. I took readings of the temperature of water in each bowl every day, at dawn and at dusk, and looked at the difference between the temperatures in the morning and in the night. I also wanted to see the temperature difference between each bowl to see if the air salt could maintain a lower temperature than the pure salt water. To conduct this experiment, I used 1 cardboard box, 2 identical bowls, 1 lamp, 250 milliliters of air salt split into 2 identical bowls, and 5 sprays of the bag-on-valve air salt at the beginning and 3 sprays each day. To simulate the conditions of the Earth correctly, I portrayed the box as the outer layers of the Earth, the lamp as the sun and the sunlight, and the salt water as ocean water. The aerosol had to be sprayed in a close proximity of the water due to it being capable of moving to the other bowl and giving me misleading results. In my experiment, I left both bowls for 9 days to analyze each bowl and changes to the temperature carefully. I observed that the highest temperature of salt water in the bowl with air salt was 24.1 degrees, whereas the highest temperature of the pure saltwater bowl was 24.3 degrees. Throughout the 9 days, the variation in temperatures between the end of the day and the start of the day was lower for the air salt bowl as against the pure saltwater bowl. Variation in temperature of the air salt was 0.2 to 0.4 degrees Celsius lower than that of the pure saltwater bowl. This meant that the air salt was able to reflect some light due to which the water temperature was lower. This proved my hypothesis correct, where, to reiterate, I stated that the bowl with the aerosol sprayed will maintain a lower temperature than the pure saltwater bowl. My experiment can help us understand how stratospheric aerosol injection might work and how it can be used to combat climate change. Extrapolating this to the entire planet, we can say that the aerosol injection method would have an impact on lowering the temperature of the Earth's surface to some extent. If there is increased focus and research in this area, we would have greater clarity on the impact of aerosol injection on countering climate change. I strongly believe that an eco-friendly solution to stratospheric aerosol injection, like the bag-on-valve technology, would make a viable solution to combat climate change and save our planet. Thank you for listening.